Welcome back, everybody. We're diving deep today into the world of open source AI and specifically OLMo 2.
Ooh, exciting.
It is, right? We got a lot to unpack. We've got the official academic paper, a study guide, and a really neat timeline that lays out how this project came to be.
Wow.
Our mission today is to figure out what makes this model tick, what makes it special, and why it's making waves.
Yeah, it's gotten a lot of attention. And one of the things that's really got me excited about OLMo 2 is its position on something researchers call the Pareto frontier.
Pareto frontier. Okay, now I know we've got some listeners who are familiar with this, but for those who aren't, what are we talking about here?
So imagine a chart, and on one side you've got performance, how good is the AI at different tasks, and on the other side you've got computational cost, how much processing power does it take to train.
Right, got it.
OLMo 2, it really punches above its weight class, and it matches or even beats models like Llama 3.1 and Qwen 2.5 while using fewer resources.
Oh, wow. So it's like getting more bang for your buck computationally.
Exactly.
So we've got these different versions, right? We got OLMo 2, 1124, 7B, and the 13B, each with its instruct model. What's the difference?
Well, those numbers, the 7B and 13B, they refer to the number of parameters in the model,
Okay.
which is a rough measure of its complexity, kind of like how many brain cells it has. The instruct models are specially trained to follow instructions.
So they're the ones you'd want to use if you're trying to, like, get it to write a poem or translate a document or something.
Exactly. They're more geared towards specific tasks.
So that makes sense. But, this is open source. They've released all their data, their code, even their training recipe. What does that mean for people actually using these models?
It's huge. It means that researchers, developers, even hobbyists can get their hands on a really powerful language model without needing, like, a supercomputer.
So it's really democratizing AI development.
Exactly. It's lowering the barrier to entry.
That's amazing. Now, let's get into some of the nitty-gritty technical stuff. You mentioned training instability. What's that?
Right. Training these massive models, it can be a little chaotic. Think of it like trying to build a tower of blocks on a wobbly table.
Okay, makes sense.
You get these sudden drops in performance, these spikes in something called the gradient norm.
So what did the OLMo team do? Did they find a steadier table?
Well, they did a few things, and one of them interesting things they did was they filtered out something called repeated n-grams from the training data.
N-grams. Give me a quick refresher.
Sure. So an n-gram is just a sequence of words, right?
Yeah.
So the cat sat on would be a 4-gram.
Gotcha.
They found that when you have these really repetitive n-grams in the data, it can mess with the training process.
Interesting.
It's almost like the model gets stuck in a loop, repeating the same patterns over and over.
And by removing those redundancies, they help the model learn more meaningful stuff.
Exactly. They made the training data more diverse, more balanced, and that led to a smoother training process.
Okay, so that's one way they tackle this instability issue. What else did they do?
Well, they also changed how they initialize the model's parameters, which is like setting the starting point for the learning process. Instead of using something called scaled initialization, they switched to a truncated normal distribution.
Ooh, truncated normal distribution. Okay, break that down for me.
Imagine you're going on a cross-country road trip.
Right.
You wouldn't just pick a random spot on the map and start driving, right? You'd want to choose a starting point that sets you up for success.
Makes sense. So choosing the right initial parameters is like choosing the right starting point for the model's learning journey.
That's a great way to put it. It gives the model a better foundation to build on.
I like that. Now, I know they made some tweaks to the model's architecture itself, things like RMS norm and reordered norm. What's the deal with those?
These are kind of like fine-tuning the engine of the car.
Oh.
Each one plays a specific role in stabilizing the training process and preventing those sudden drops in performance.
It's amazing how seemingly small adjustments can have such a big impact on the model's overall performance.
It is, and it speaks to the level of care and attention that the OLMo team put into this project.
Absolutely, but I feel like we're just scratching the surface here. What other tricks did the OLMo team have up their sleeves? Because I know there's more to this story.
There is, and one of the most intriguing aspects of their approach is something called mid-training, this 2-stage training process that really sets OLMo 2 apart.
Intriguing indeed.
So we left off talking about mid-training.
Right. This mid-training thing, it's where the magic happens, right? What is going on there?
Yeah, it's pretty cool. So you can think of pre-training as like giving the model a broad education, exposing it to a ton of text data, mostly from the web, so it gets a good grasp of how language works.
So like sending it to a good liberal arts college?
Exactly. But then mid-training, this is where it gets specialized.
Okay.
Instead of just feeding it more of the same, they curated a special mix of high-quality sources, including this thing called Dolmino Mix 1124.
Dolmino Mix, that's a fun name.
Right. We don't know exactly what's in it. But the results are incredible. You look at Table 9 in the paper and you see this jump in performance on all sorts of tasks. Knowledge questions, reading comprehension, even math skills.
Wow, so it's not just the quantity of data, it's the quality too.
Exactly. It's like supplementing that liberal arts education with specialized courses.
I love that analogy.
And to make sure they're choosing the right stuff for this mid-training phase, they use this technique called microannealing.
Microannealing. Okay, that one sounds a little technical. What's that all about?
Well, it's kind of like if you're a chef experimenting with a new recipe, right? You wouldn't just dump everything in the pot all at once.
Right.
You might try little test batches to figure out the best proportions, cooking times, that sort of thing.
So they're basically running mini training experiments to see how different data sources affect the model before they commit to the whole thing.
Precisely.
Yeah.
It's all about optimizing that mid-training process, getting the most bang for your buck.
That's clever. But we've talked about training data. We've talked about architecture. How do they actually get the model to like follow instructions and do what they want it to do?
That's where post-training comes in. They have this 3-phase process inspired by a model called Tülu 3, but with their own twist.
3 phases. Okay, lay it on me.
So the first phase is supervised fine-tuning, or SFT, where they basically give the model a bunch of examples of what they want it to do.
Okay, so instead of just letting it read everything it can find, they're giving it specific lessons.
Exactly, like teaching a student how to write different types of essays.
Right.
You give it input-output pair so it learns the format, the style, the level of detail.
Makes sense. But I'm guessing SFT isn't enough.
Nope. Phase 2 is preference tuning with direct preference optimization, or DPO.
DPO. All right, break it down.
This is where they bring in another AI, actually GPT-4 in this case, to evaluate the model's responses.
Oh, wow. So it's like having an expert judge giving feedback.
Exactly. They're looking at things like helpfulness, truthfulness, honesty, and how well the model followed the instructions.
Interesting. So it's learning to align its responses with what humans prefer.
Exactly. And then comes the final phase, the most innovative one, reinforcement learning with verifiable rewards, or RLVR.
RLVR, this sounds intense.
It is. Now the focus is on specific tasks where the answers can be objectively verified.
Like math problems or fact-checking.
Exactly. The model only gets rewarded if its output is demonstrably correct.
So it's not just about sounding good. It's about being right.
You got it. It's all about training for accuracy and precision.
That makes sense. But to do all of this, you need some serious computing power, right? I mean, these models are huge.
You're telling me. And the infrastructure behind OLMo 2 is a story in itself. It's not just about brute force, though there's definitely some of that, but it's about smart choices and a hybrid approach.
Hybrid approach. Intriguing. So a hybrid approach to infrastructure. Tell me more about that.
Well, they actually use 2 different computing clusters. First, there's Jupiter, their own dedicated cluster down in Austin, Texas.
Oh, wow, their own setup.
Yeah, it's got over 1,000 NVIDIA H100 GPUs, all linked together with a crazy fast interconnect network.
Wait, H100 GPUs, those are like the top-of-the-line chips for AI, right?
Absolutely, they're the gold standard. And it's not just about the GPUs themselves. The whole cluster is designed with this super advanced cooling system to keep everything running smoothly, even when they're pushing it to the limit.
So they really went all out.
They did. But then they also tapped into the power of the cloud with Augusta, their Google cloud-based cluster.
Okay, so Jupiter's the powerhouse, and Augusta's the cloud backup.
More like a dynamic duo. Augusta uses Google's A3 Mega virtual machines, which also have those H100 GPUs.
Oh, wow.
Being able to use both of these clusters really highlights how portable and adaptable their training pipeline is.
It's like having a mobile command center for AI development. They can deploy their resources wherever they need them.
Exactly. Now, managing all this infrastructure can be a real headache, right?
Oh, yeah, I bet.
But they use this system called Beaker, AI2's own workload management system, and it's kind of like the conductor of an orchestra, making sure everything's working together in harmony.
So Beaker takes care of all the logistical stuff so the researchers can focus on the science.
Exactly. It handles things like allocating resources, scheduling jobs, and even monitoring the health of the GPUs to prevent any hiccups.
That's smart.
Yeah, and they even mentioned this cool feature where Beaker will automatically quarantine any malfunctioning GPUs so that training jobs only run on the good ones.
It's pretty impressive.
It is. It really helps to maximize efficiency and keep things running smoothly. Now, of course, all of this comes at a cost, right? Not just financially, but also in terms of energy consumption and environmental impact.
Right. That's a really important consideration these days.
Yeah, and the OLMo team's very aware of that. In fact, they dedicated a good chunk of their paper to talking about how they're trying to minimize the environmental footprint of OLMo too.
Good for them. So what did they do specifically?
Well, a big focus was maximizing how they use the hardware, optimizing their code for efficiency.
Okay.
They even gave detailed estimates of the energy consumption and carbon emissions for the whole training process.
That's really impressive. It's good to see that level of transparency.
Yeah, it really is.
Now, I have to ask, with all this talk about technical details, what does this mean for the average person? How could OLMo 2 actually impact our lives?
It's a good question. The possibilities are really endless. Think about more personalized education tools, more intuitive ways to interact with technology, maybe even breakthroughs in scientific research that we can't even imagine right now.
It's exciting and a little bit
Welcome
daunting
back,
at the same
everybody.
time,
We're
right?
diving
Absolutely.
deep
It's like
today
opening a
into
door
the
to
world
a
of
whole
open
new-
source AI and specifically OLMo 2.
Ooh, exciting.
It is, right? We've got a lot to unpack. We've got the official academic paper, a study guide, and a really neat timeline that lays... Hey there. Want to share your thoughts on this? Welcome back, everybody. Welcome back, everybody. We're diving deep today into the world of open source AI and specifically OLMo 2.
Ooh, exciting.
It is, right? We've got a lot to unpack. We've got the...
Oh, hey, our listener wants to join in. What's up?
Hey there. Can we wrap up the key points of this study in the beginning?
Well, that's a great point, listener.
Yeah, it really is. And it's something that can get overlooked sometimes.
When you're working with something like AI, it's easy to get lost in the details, and we're definitely going to get there. Don't worry.
Yeah, we will. But you're right. It's key to know why this matters in the first place.
Exactly. So let's break down what's so important about OLMo 2 for getting started.
Okay, let's do it. It's all about that accessibility.
Yeah, it's designed to be open source so anyone can get their hands on it.
Right. And not just the code, but the data and even the recipe. That's the training process.
So you have a level playing field to start with when compared to other big AI models.
And it's not just about access, but also about performance.
Absolutely. OLMo 2 really punches above its weight class, and it matches or even beats models like Llama 3.1 and Qwen 2.5 while using fewer resources.
Oh, wow. So it's like getting more bang for your buck computationally.
Exactly, which is huge when you're first getting started.
So we've got these different versions, right? We've got OLMo-2, 1124-7B, and the 13B, each with its instruct model. What's the difference?
Well, those numbers, the 7B and 13B, they refer to the number of parameters in the model,
Okay.
which is a rough measure of its complexity, kind of like how many brain cells it has. The instruct models are specially trained to follow instructions.
So they're the ones you'd want to use if you're trying to like get it to write a poem or translate a document or something.
Exactly. They're more geared towards specific tasks, and you can start experimenting with those right away.
That makes sense. But, this is open source. They've released all their data, their code, even their training recipe. What does that mean for people actually using these models?
It's huge. It means that researchers, developers, even hobbyists can get their hands on a really powerful language model without needing, like, a supercomputer.
So it's really democratizing AI development.
Exactly. It's lowering the barrier to entry, which is critical when you're just getting started.
That's amazing. Now let's get into some of the nitty-gritty technical stuff. You mentioned training instability. What's that?
Right, training these massive models, it can be a little chaotic. Think of it like trying to build a tower of blocks on a wobbly table.
Okay, makes sense.
You get these sudden drops in performance, these spikes in something called the radiant norm. They had to fix this to even get started.
So what did the OLMo team do? Did they find a steadier table?
Well, they did a few things, and one of the most interesting things they did was they filtered out something called repeated n-grams from the training data.
N-grams, give me a quick refresher.
Sure. So an n-gram is just a sequence of words, right? The cat sat on would be a 4-gram.
Gotcha.
They found that when you have these really repetitive n-grams in the data, it can mess with the training process.
Interesting.
It's almost like the model gets stuck in a loop, repeating the same patterns over and over.
And by removing those redundancies, they help the model learn more meaningful stuff.
Exactly. They made the training data more diverse, more balanced, and that led to a smoother training process.
Okay, so that's one way they tackled this instability issue. What else did they do?
Well, they also changed how they initialize the model's parameters, which is like setting the starting point. Yep, go on.
Can we talk about the creative intuition of this study?
Absolutely. That's a great question, listener.
Yeah, it's really important to understand how they framed their study.
So they weren't just aiming to build any language model. They had specific goals in mind.
Right, and that influenced all the decisions that they made, from data curation to the evaluation process.
Exactly. The introduction of their paper makes it clear that their main goal was to create a high-performing open source model that is also stable.
And I think that really underscores the importance of the why behind all of this technical work.
Precisely. And it also shows that their criteria were not just about achieving high scores on leaderboards, but also making sure that it's accessible.
Okay, so when they're talking about these goals, what does that mean in practice?
Well, for example, you'll see them really emphasize data quality throughout the paper, which we'll touch on again later. And this is one of the biggest components of their criteria.
Okay, so it was important that the model wasn't just learning from any old text, but from high quality sources.
Exactly. They did a ton of work filtering out noise and repetitive content like those m-grams, because that directly relates to the stability of the model.
And you mentioned stability was also one of their explicit goals, right?
Yes, and that is why they focus so much on things like RMS norm, QK norm, and Z-loss, all of which are designed to prevent things like training crashes.
Now, we've talked about all this. I think it's clear the criteria really does shape how the project was developed.
Yeah, and that goes for how they set up the evaluation of the model as well.
Which is something we'll definitely dig into in a bit to see how well they met their goals.
Absolutely. So that's a really helpful way to frame all of this.